So next up, we have a talk called Goodbye GIL, exploring the free-threaded mode in Python 3.13 with Adarsh Divakaran. He's an experienced developer in APIs and is currently co-founder and lead consultant at I didn't even check how to say that, Diego Labs. So welcome, Adarsh. Thank you.
Hi everyone, good morning. So today we will be exploring the free-threaded mode in Python 3.13. So I am joining this year's PyCascades from Kerala, India. I am Adarsh Divakaran. I am the co-founder at LinkageQ. At LinkageQ, we are building a super app for the creator economy. So let's move on to today's topic. So today we'll be starting with the global interpreter lock in Python. Then we will explore the free-threaded version of the Python interpreter introduced in Python 3.13, and we will do some demos and performance benchmarking of different type of code like single and multi-threaded CPU versus IO bound, etc. So let's start with getting to know the global interpreter lock. So as the name suggests, it's a lock. It's a mutex in CPython, preventing multiple threads from executing Python bytecode simultaneously. So this is a lock which allows only one thread to execute Python bytecode at a single time. So it was introduced to simplify CPython's memory management and the C extension API, but it came with its own set of limitations. Like it limits true parallelism for CPU bound tasks, and in case of IO bound tasks, they are less affected as the GIL is released during IO operations. So in case of CPU bound workloads, historically, we used to use multiprocessing as our concurrency primitive. But with multiprocessing, there comes additional complexity, like the variables or the memories are not shared. So we have to do some inter-process communication, and multiprocessing comes with its own set of problems and additional complexity. So PEP 703 was proposed to make the global interpreter lock optional. So it proposes making the GIL optional in Python, and it introduces a free-threaded build. So in the free-threaded build, the GIL will be disabled, and it aims to unlock true parallel execution for CPU-bound workloads. Now, the free-threaded builds started coming out with Python 3.13, and the eventual goal is to combine both releases. And there has been some issues with the release. There is some issues for C extensions. Since we are breaking the global interpreter lock, many of the code were written assuming that the global interpreter lock exists. So there will be some breakages related to external libraries and C extensions. And there has to be some performance overheads, which can affect single-threaded code. So we'll be exploring them through our demos. Next, let's look into setting up free-threaded mode. So on this page, you can explore the installation options. So if you are building from the source, we can use this disable GIL flag to build the CPython free-threaded version. And one of the most commonly used version is we can use the official installers from python.org for Windows and Mac users. You can download the official installers, which comes bundled with free-threaded mode. Next, for Ubuntu, we can add this repository and we can install using the below comments. Next, once this interpreter is active in our system, we can use the executable to start a virtual environment, to create a virtual environment with the free-threaded interpreter. Next, we can verify whether the free-threaded mode is working by using these two setups. We have our sys module, And sys module has a new attribute, is GIL-enabled. And we have a config variable in sysconfig module also. So we'll be exploring them in our demo. Now let's move on to the interesting part. Let's run some demos and benchmark the performance. Before that, let's think of the changes that were happened. So according to PEP 703, the implementation changes approximately 15,000 lines of code in CPython. So it's a big change, and it introduces a new memory allocator, which is approximately 15,000 lines of code. So next, we'll be moving to our benchmark section, and we will be comparing the execution time of pre-threaded interpreter versus the GIL-enabled default interpreter of Python 3.13. So let's start with a single-threaded program. We'll be using a simple math operation, and we will compare the performance of the different interpreter versions. So I have my demo set up here. So in the first demo, let's check the global interpreter log status. So we have two methods in our sys module as well as sysconfig module. In the sys module, we have this attribute is GIL-enabled attribute, and from the sysconfig module, we can get the config variables, and we can see if this config variable is set or not. So let's try the setup. Now I have like 3 different interpreters set up in my system. You can see I have a Python 3.12, and I have 3.13 with GIL-enabled, which is the default Python interpreter. And I have my free threader interpreter also ready. Let's start with the 3.12 version. If you are running this, this will raise an error since this attribute is not present in Python 3.12. But we will get the value of this config variable. We are using the get function to fetch the data from the dict-like object. So we can see that this config variable is coming out as none, and this attribute is missing in the interpreter. So let's move on to the default global interpreter log enabled interpreter. So we can see that the GIL disabled is 0, which means that the global interpreter log is enabled, and we are running the default interpreter. Next, let's move to the free threaded version. So here we get the GIL disabled value as 1, and is GIL enabled is false. This means we are running the free threaded interpreter. So let's move on to our first example, so which is a single threaded code. So we are using Python's timeit module to execute this code. So we are just calculating the sum of numbers up to 1 million. We are initially displaying the global interpreter log status, and then we will run this testing code. This will be run using the timeit function, and there will be 100 repetitions, and we are printing the execution time. So let's try it with the global interpreter log enabled default version. So you can see the message that the default interpreter is used, and we have 3.95 seconds. Let's do it once more. So it's like 3.9. We got 3.9 seconds initially, 2.9, and I think we can conclude the average as around 3.0. So this is the GIL-enabled interpreter. So we are getting like execution time of around 3 seconds. Next, let's execute the same code with our free threaded interpreter. Let's do it once more. Initially, we got 4.7 seconds. And next, we got 4 seconds. Then we got 3.8. So it's like around 3.8 or 3.9. So this is the benchmark result of a single threaded program. So we have used a computation and we used a single thread. So we got a better time, like the operation completed in just 3 seconds in the default interpreter, and it was slower on the free threaded version. So this is expected. Like for single threaded programs, free threaded mode has a negative impact on performance. Like in our case, in the free threaded mode, the global interpreter lock is disabled. So to ensure thread safety, there have been some additional code or additional complexity in case of single threaded programs. And this will negatively affect the performance in the current version. So if we are just using single threaded programs, or if we are not planning to have multiple threads in our application, it will be better to go with the default interpreter. And the free threaded version will not be useful in our case. Next, let's go for a CPU bounded program. So in case of a CPU bounded program, we'll be performing a computationally intensive operation. And we will perform two variations, like we will execute the same in a single thread, and we will execute the same in multiple threads. Then, like we did previously, we will benchmark the results and performance. So let's go with this. So we are performing this execution 50 times. And we have a calculate function. So this is the CPU intensive operation we will be performing in this benchmark. So we are calculating squares of numbers till 10 raised to 7. And we are performing two executions. Like we have a multi-threaded function. So we have a thread pool executor here with 10 worker threads. And we will repeat 50 times. And we will call the function totally 50 times using 10 worker threads. And we are also checking the single threaded performance. We are just for the same execution count without using any threads. We are calling the operation 50 times. Then we will move on with the multi-threaded execution. So let's start with our free threaded version. So you can see that the global interpreter lock is disabled, and we got 3.7 and 1.3. So for 50 executions, we can see that a single threaded execution totally took 3.8 seconds, whereas the multi-threaded execution took around 1.38. So this is our CPU bound program. Single thread took 3.8 and multi-thread took 1.38 in our free threaded interpreter. Now let's move on to the default interpreter. GIL is enabled. We can see that the execution time comes around 5 and 3.4. Let's try that once more. Both of these comes around 3.6 this time. So we can consider this as 3.6 and 3.5. So we got the single thread execution time of GIL-enabled interpreter as 3.6, and we have the multi-thread execution time as 3.54. So you can see that in case of CPU bounded multi-threaded code, we are getting great performance improvements if you are using the free threaded interpreter. This is because previously, in case of CPU bound programs, we had the global interpreter lock. Only one thread could execute parallelly, truly at the same instance. But with the free threaded build, they can achieve true parallelism, and we are achieving more than a 2x speed up here. Next, we can move to an IO bounded program. So we'll be performing an IO operation. For example, we can do some network calls, or we can write to a file, and we can do a similar benchmark also. So this is our IO bound program. We are opening a temporary file, and we are performing some write operation, seek, read, and finally we are removing the file using os.remove. So we are performing file manipulation in this example, and we have two functions. Single threaded function, it calls operations one, and for the multi-threaded, we are using 5 workers, and we are calling that 5 times. Next, this is our benchmark code. So we are benchmarking the time for single-threaded and multi-thread execution. In this case, we are calling the single-threaded function 10 times, and we are calling the multi-threaded code 4 times. And inside this, we are creating 5 threads. So there will be total 20 times, 20 calls in the multi-threading scenario and 10 calls in the single-threaded scenario. So now let's run that with the default interpreter first. So the single-threaded execution time took around 5.5, and the multi-thread took 5.14. So I think we can consider as an average. The single-threaded time was 5.6 seconds, and the multi-threaded as 4.3. So there are some minor variations, like we are getting values around 4.3, 4.8, and 4.9, 5.6. Now let's move on to the free thread interpreter. GIL is disabled. We are initially getting 6 and 5.3 seconds. So these are also varying around 3, 5, and all. So in this case, when we are executing multiple times, we can see that most of these results are comparable. Like these are IO bound operations. So in case of IO bound operations, the global interpreter lock is automatically released. So it's expected that the performance will be comparable in an IO bound scenario, and we are not getting any speed up like we have seen for CPU bounded tasks. So we can conclude that for IO bound tasks, the performance will be very nearly comparable, and there won't be much speed up if you are using the new free threaded version. Next, we can move to a web application, WSGI example using a Flask application. So we will be defining two API endpoints, one running IO bound operation and other running CPU bound operation. And we will benchmark the performance like we have did previously. So let's first run our app. So we have our free threaded mode initially. We can see that the code is running in free threaded mode, and we have our Flask app running on port 5000. Next, I have some benchmarking code set up here. I will run this benchmark now. I'm using a tool called K6 to perform the benchmarks. So we will start with the CPU bounded benchmark. So it creates 15 virtual users and it sends a request to our endpoint. So now let's take a closer look into our Flask application and the different endpoints. We have a CPU bound endpoint. So it calls a function. It's the same function we have used previously. It calculates the sum of numbers, sum of squares up to 10 raised to 7. So this is our CPU bound task. And right now we are sending request with 15 virtual users for 20 seconds to this CPU bound endpoint. So we can see there has been 80 requests, 80 HTTP requests has been sent in a duration of 20 seconds. So we are using free threaded mode. So we got 80 requests in 20 seconds. Now let's perform the same for IO also. This is our benchmarking code. So it hits this endpoint, our API endpoint. There will be 15 virtual users and the total duration is given as 20 seconds. So this is complete. We got 66 requests in 20 seconds. Next, let's move to the default interpreter. And let's start the CPU bound benchmark. So in case of a Flask application, Flask by default runs the application in multiple threads. So I think in my system, it's running 2 threads. So it's a multi-threaded application. We can consider our API or web application as a multi-threaded application. And here we can see in the default interpreter build, we get 83 requests in 20 seconds. Next, we can run the benchmark of IO operation. Sorry, let's rerun a Flask application. I think it was the same one. Yeah. Yes. Right now, we have the default interpreter. The Flask app is running with GIL-enabled. Now let's redo that. We are getting similar results. Like we got 83. We got comparable requests because it was the same server. Let's run this again. Next, currently we are running the CPU bound task benchmark. Then we have the IO bound benchmark also. This is also the code we have seen previously. For simulating the IO, we are writing to a temporary file, and we are finally trying to remove that temporary file. So this is complete. You can see that only 36 requests can be sent in 20 seconds in the global interpreter lock enabled build. Now let's try the benchmark for IO also. As I have said previously, we have Flask, which runs multiple threads. The Flask API is run using multiple threads in our system. So it is a multi-threaded app, and we can see that for a CPU bounded program in a multi-threaded setup, we are getting about more than 2x speed up or more than 2x performance in our case. And for this endpoint, we get IO bound application, we get around total 95 requests. 95 requests in 20 seconds. So the performance hits maybe this the performance hit in case of the IO bound may be request maybe due to the overhead of a free threaded build. But when we are considering the CPU bound endpoint, we are getting more than 2x performance benefits in our case. So let's look into the summary. So this is a previous screenshot. I think the case is the same here. For CPU bounded multi-threaded code, we are getting great speed up for pre-threaded build. You can see in case of CPU bound multi-threaded normal script as well as the WSDA application. Now let's look into the migration checklist. If you are looking to move to a pre-threaded build, it is great for CPU bound tasks plus multi-threaded code. Then great for scenarios where parallelization is required, but multiprocessing is too complex or the cost associated with inter-process communication is not bearable. Then if you're moving to a free-threaded build, you need to check third-party library compatibility also. There have been some libraries which has compatibility issues with the free-threaded mode. Next, according to PEP 703, right now we have a GIL-enabled version as default. This can be changed in a future release. And the great news is that in future, the performance penalties will be reduced for the free thread interpreter when run on a single thread. Right now, we are seeing some performance hit if you are running single threaded program. So in the future, we can optimistically think that the performance hit will be less, and we can move to a truly global interpreter log free build by default. So yeah, that's it. If you have single threaded programs, we should go with the default interpreter. And if you are using multi-processing as our program as our concurrency primitive, we can go with the GIL disabled. If you are using multi-processing, there won't be any benefit using the free threaded interpreter. But the great improvement can be seen when we have CPU bounded programs which are running in multi-threaded environments. So previously we were unable to use this CPU bound programs with threading. There were no performance improvements, but for Python developers, we are now seeing a new concurrency mode is being unlocked for us if you are using the free threaded build. So that's it. You can get the talk slides and the code, and you can connect with me using the following link, linkhq.co/Adarsh. Thank you. Thanks, everyone.